Hello everyone, in this video let's look at the Lagrange error bound. So this can be also called as the Lagrange error theorem or the Taylor's remainder theorem. So basically, in order to approximate a function precisely as what we have looked at in the past, we can express it as an infinite polynomial, or so f of x is equal to some sort of infinite polynomial. Or alternatively, we can express it as a Taylor polynomial of a few terms, Tn x plus the remainder, Rn of x. So basically what this expression means is that we can express the function as the Taylor polynomial plus the remainder. So if a function is supposed to go to this place, we can have the Taylor approximation go up to here, and the rest is the remainder. So T just represents a Taylor polynomial with n terms. Let's write it down. Taylor polynomial with n terms. And then this is just the remainder after n terms. So if this is a1 plus a2 plus blah blah up to an, then this remainder is actually equal to an plus 1 plus an plus 2 plus all the way maybe up to infinity. So in order to find the value of the error r of n, we just use the Lagrange error bound to try to find the upper bound of the error. So this expression looks a bit complicated. So let's just see what it looks like. Firstly, Rn is the remainder or the error, and we take the absolute value because our approximation can either be over or under the real value. So our if this was a real value, our approximation can go over it. So this is Tn of x, and then our error will be negative. So this is why we take the absolute value. So that's Fn. And what about n plus 1 over z? So it's not like we have to raise it to the power. This is just the notation of the derivative. So this is the n plus 1th derivative of f of x. And basically, z is some value between a and x. So if we have an interval with a function, let's just say if there is a function, and then in this interval a to x, there will be a value z. So z is within the bounds because this is where we are trying to make the approximation, and there's a probability that the n plus 1th derivative at z will be the maximum value of all derivatives of the function in the range a to x. So it's actually the n plus 1th derivative, and we can just think of it as this way. So if we have a larger derivative, then the error will be higher. Let's just think of a normal linear approximation. So let's just think linear approximation. And so if we have a slightly concave up curve or a very concave curve, and then if we try to make an approximation, we will find out that this one that has a smaller second derivative of x has a smaller error, which is why in order to find the bound, which is the maximum error, we just want to find the largest value of the derivative, so that's just an analogy. And then we look at other parts of the equation. We see that x is just the given x value because often we want to find the error bound when we are, for the value of x we are approximating. So x is just like the input, and then a is where the polynomial is centered. So like recall that like these power series are centered around the values, and if it's centered around x minus a, it means like a is there, and we just use the same, and we raise it to the n plus 1th power, and then we divide it all by the degree of the polynomial plus 1 factorial. So let's try an AP style question to test out our skills. Over here we want to approximate cosine 1.3 pi with the Taylor polynomial at x is equal to 1.5 pi. So it means that it's centered at x is equal to 1.5 pi, or a is equal to 1.5 pi. And what's the least degree of the polynomial? So we remember that in our expression f of x is equal to this plus Rn of x, and in this case f of x is 1.3 pi plus, which is equal to Tn of 1.3 pi plus Rn of 1.3 pi. And if it's only asking for the error bound, we just need to focus on this one, which is the error R of n. And we just want to apply the Lagrange error bound. So Rn of x, absolute value, is smaller than, if we look at the top, it's f to the n plus 1 over of d times x minus a to the n plus 1 over n plus 1 factorial. And we know that it's centered around a is equal to 1.5 pi. And then we can look at the value for the maximum derivative. So we recall that in the cosine function, even if it's like not bounded in the interval, the maximum like derivative or slope is equal to 1. So we can just replace this expression with 1, and a is equal to 1.5 pi. So we can just rewrite everything as 1 times 1.3 pi, because we are taking the approximation of 1.3 minus 1.5 pi to the n plus 1 over n plus 1 factorial, which is smaller than 0.001. So after taking the absolute value, it's around 0.2 pi to the power of n plus 1 over n plus 1 factorial is smaller than 0.001. And we can't really don't really have an easier method to solve for it, so we can just try out some numbers, plug it in. If it's n equals to 1, it's 0.628, and if n is equal to, just continue trying, and we find out when n is equal to 3, it's equal to 0.06 something, but when n is equal to 4, it's 0.00082, which is smaller than 0.001. So we see that when the degree gets larger, the error becomes smaller, which makes intuitive sense, because if you have more terms to calibrate the Taylor polynomial, it will fit the curve better. So our answer is the fourth derivative, because when n is equal to 4, the error is less than 0.01. Yeah, so in conclusion, it must be at least to the degree of 4.